In a previous video, I explained how to do stoichiometric calculations, and in that example, I converted masses to moles and then converted the moles back to masses. That is another way of doing stoichiometric calculations, especially when you want to calculate the amount of products produced or the amount of reactants used or required. In this video, I'm going to do the same calculation using first principles. This is quite a straightforward method. It is also fast and efficient. I'm going to use the same example where we are calculating the amount of carbon dioxide produced when 2 kg of ethanol is burned completely. I want to emphasize that whenever you are given a question, listen to what the question is saying. Like in our case, when they are saying burned completely, it means there was enough or sufficient oxygen to burn all the ethanol that was there. It also means the product of our reaction obviously will be carbon dioxide and water, because if there is incomplete combustion or incomplete burning, we produce carbon monoxide. So the word completely here has a very significant meaning. Now let me go to the steps that you have to take when using this method. Just like the previous method, the first thing that you do is to write the reaction equation and balance it. Then after that, you calculate the molar mass of each reactant or end product, and then you multiply it by the coefficient, which is essentially your stoichiometric coefficient from your balanced chemical equation. Then you divide throughout. In other words, you're dividing these masses that you calculated in step 2, you are dividing them by the total mass of one of the reactants or products. Now, if you do that, you're going to have smaller numbers that you're going to work with, which you can use as ratios, mass ratios per se. In the previous video, I used mole ratios. In this video, we're going to use mass ratios. So once you know the mass ratios, you can easily calculate the amount or the mass produced or the mass of a reactant that has been used or that is required. It becomes very, very straightforward. So let us move straight to the solution of this equation. Let us do step 1, which is writing the chemical equation. It is ethanol, which is C2, so C2 here, H5 or H. It is combustion, so we are adding oxygen, and it is complete combustion, which means our product are carbon dioxide plus H2O. I'm just going to quickly balance this equation. If you have forgotten, this is how you do it. On the left hand side, we have 2 carbon atoms. On the right hand side, we got 1, so we multiply here by 2. This is called a stoichiometric coefficient. We don't change our chemical formulae, we just multiply by stoichiometric coefficients. And the coefficients can be whole numbers or they can be fractions. Be free to use decimals or fractions, it is allowed. Now let us balance hydrogens. To the left hand side, we got 6 of them, and to the left hand side, we have 6 hydrogen atoms. To the right hand side, we have 2. We multiply here by 3. And lastly, we balance oxygen, which is the element. We always balance our element last. It makes it easier to balance the chemical equation. Now we have 7 oxygen atoms to the right hand side, and to the left hand side we got 3, but if we multiply here by 3, we now have 7, which is the 6 here plus 1 here, then we have 7. The equation is now balanced, which means we have done our step number 1. Now the second step is to calculate the molar mass of each of our reactants, and we multiply it by the coefficient behind it. I'm going to do that quickly. The molar mass of ethanol is 46. We calculate it by adding. Let me just show you an example of how we do this. Let's say for ethanol, which is C2H5OH. If we want to calculate the molar mass, it is 2 times 12. 12 is the molar mass of carbon, and we have 2 there, plus, I see here we've got 6 hydrogen atoms, which means we're going to multiply 6 by 1, which is the molar mass of the hydrogen as an element, plus 16, which is the molar mass of an oxygen atom. We add this, we get the molar mass of ethanol itself. So it is that is 46. So we get 46. You do the same for all of the products and all of the elements. Take note that all these numbers I'm using here, I'm getting them from the periodic table. They are always there on the periodic table of elements. And this is where you get these molar masses. If you don't know how to do it, I'm going to do another video where I explain how to calculate the molar masses and the relative molecular masses, etc, etc. All right, let us clear our board. All right. Now I'm going to do the calculations now. So for ethanol, it is 46. And we're multiplying it by 1. So it's like 1 times 46. Let me wrap this. It's 1 times 46. So it's 1 times 46. I'm saying 1 because the coefficient there on ethanol is actually 1. We don't write the 1, but it is there. Then plus, for oxygen, oxygen molecule, this is 2 times 16, which we get as 32, and we multiply the 32 by 3. So it's 32 times 3, we get 96. So this is 96 here. All right. Let me remove this. There's no need for me to write this one. I'm just going to write it as it is. I just wanted to illustrate how you calculate these masses. So that was 96. On the right hand side, we got 2 times carbon dioxide. The molar mass of carbon dioxide is 44. We are multiplying it by 2. So we get 88. So this is 88. Okay, let me use a green pen. So this is 88. And for water, it is 18 times 3. That is 54. These are the masses that I said. You calculate these masses. So we got 46 and that and 96, 88 plus 54. What I want to tell you is, because during a chemical reaction, mass is conserved. If you add the masses on your left hand side, they should also be equal to the masses on the right hand side. They should be. If they are not, it means you didn't do your calculations properly. So if you look here, they are equal. This is a step number 2, where you calculate the total masses of each. So we're calling this the total masses. They're actually total masses because we are multiplying our molar mass times the stoichiometric coefficients. What this equation is saying, or what these numbers are saying, it is essentially saying if you've got 46 grams of ethanol, it requires 96 grams of oxygen to produce 88 grams of carbon dioxide and 54 grams of water. It doesn't matter also if you say it in kilograms. It also means 46 kgs of that. So I'm going to use kgs in our case because my question was saying I got 2 kgs of ethanol. That's why I'm going to call this as kg. So these are kilograms. So this is kg. This is kg. So I can interpret it in terms of kg. Guys, it doesn't matter. whether it is the combustion of sulfur or the combustion of carbon or the combustion of any other element, the approach is the same. Or even if it is not a combustion reaction, the approach is the same when you're doing it from first principles. So now I can say if you have 46 kgs of carbon of ethanol, you need 96 kgs of oxygen to produce 88 kgs of carbon dioxide and 54 kgs of water. Now I'm going to divide by 46 throughout. I'm doing this division so that I can have, so divide by 46 throughout. So each of these masses, I'm going to divide it by 46. If I do that, for the first one, I get 1. These are mass ratios now. These are actually mass ratios. And 96 divided by 46, I get 2.087 to 3 decimal places. Then 88 divided by 46, I get 1.913. Then 54 divided by 46, once again, I get 1.174. 1.174. What we have here are still mass ratios. These are mass ratios. So what is the mass? What are the mass ratios saying? They are saying if you have 1 kg of, so let me put the units. So if I have 1 kg of ethanol, it requires 2.087 kilograms of oxygen to produce 1.913 kilograms of carbon dioxide and 1.174 kilograms of water. I'm just using now smaller ratios. These are smaller ratios. So in our case, we have 2 kgs. So now we have 2 kg here of ethanol. We want to know how much of this, of carbon dioxide. See, it's now a very straightforward issue. We know that 1 kg produces 1.913. 2 kgs obviously will produce double of that, or 2 times this one. This is the reasoning behind. So now we can conclude our question. Therefore, mass of CO2 produced, it is equals to 2 times 1.913. We get our answer in kilograms because all our units here are in kilograms. So it's 2 times 1.913. We get 3.826 kilograms. If you check the previous video that I did, you're going to find that I got the same answer using another method. This is the method of we're calculating here from first principles. It's a very, very straightforward method because all the information that I'm using here, it is available to you. It's readily available to you on the periodic table. You don't need to do any conversions from mass to moles and back to mass. No, you just do it straightforward. The mass ratios that I have here are very small and you can use them easily. Like here, if I want to know the amount of oxygen required, it will simply be 2 times this one, because this is a ratio of 1 to 2.087. So if I have 2 here, I just multiply this by 2. Anything that I want here, I just multiply it by 2. If I know the amount of of ethanol, I can use it to calculate the amount of any product or any reactant. Otherwise, that's it. You can do more examples, try to practice. If you have any questions or any comment, just write in the comment section below. Otherwise, thank you for watching the video. Give it a thumbs up and subscribe to the channel.